Good day, everyone. I am Riz Divino, an aerospace engineering student of Indiana Aerospace University, together with my colleague Christian Dave Beltran, and we are here to present to you our research entitled The Design Implementation of a Teensy-based Avionics System for Model Rockets. Avionics system is the rocket's brain. Without it, trajectory is unsure, landing is unsafe, and for some, rocket might not work. So it must be done with accuracy. However, in model rockets, it is not that complicated, but advances are fast approaching, and that flight computer must cope up with that development. Commercial flight computers are limited in functionalities and many restrictions, and even costly. That is why I introduced to you a more flexible, efficient, bigger capacity, less costly, and a reliable avionics system, the Teensy-based flight computer, an avionics system for model rockets. Firstly, let me present to you the components included in this flight computer. The microcontroller, wherein the program was coded, it is the Teensy 3.5 development board that uses Arduino software program that has a faster processing data and a larger storage capacity in a tiny sized module. It is where the other components is connected to. Also, it already have a built-in SD card slot that is programmable and can be used to save data. The next one is the barometric pressure sensor. Uh, this would help us detect ambient pressure and identifies the altitude of the system. As the pressure decreases, the altitude increases. It is an MS5611 barometric pressure sensor that has an accuracy of plus minus 1.5 millibar. The global positioning system used is the SAM M10Q GPS module. It is an advanced, accurate GPS that only uses a low power consumption without compromising its full performance. Its confidence accuracy is 95%. We are able to demonstrate the orientation of the system in any specific time using a BNO 055 inertial measurement unit sensor. This reads gravity, accelerometer, magnetometer, and gyroscope. Using Kalman filter, we are able to measure a smooth acceleration, angular velocity, and 3D orientation of the object. The components that sends the collected data to the ground station is the APC-220, having a working frequency range of 418 to 455 megahertz. This transmits a maximum of 1 kilometer in a line of sight. A Foxeer FPV video camera that captures momentous events that has a low power consumption. This is the best option to build in the avionics system since it is a high quality video in a very small form factor. In order to save and send the video data, we use the digital video recorder and the video transmitter. The digital video recorder constantly saves the data recorded, the video recorded. Then the video transmitter sends the video data to the ground station to be able to be viewed. The commercial flight computer we use to be compared with is the Missiles Work RRC-3 Rocket Recovery Control 3. This also contains a barometric pressure altimeter and has a dual ejection system and an extra auxiliary for multi-stage ignition system. This has the capability of 4 megabytes flash memory to save the flight data. Presenting the diagram on how the Teensy-based avionics system works, all the sensors data, sending it to the Teensy microcontroller, processes it, and saves to the SD card module or sending it to the ground station using the APC-220. This is the schematic diagram of our flight computer. This is the video recording system schematic diagram. From the camera, sending the video signal to the digital video recorder and saving it to the SD card. Then, directing the video signal to the video transmitter and send it to the ground station to be able to be viewed. So from the ground station, the data sent, there is a video receiver that in the ground station to be viewed on a computer in a real time. Also, the sensor data uses a similar APC-220 in the ground station and convert it to the USB and plug it in a computer using a serial port utility and be viewed and save all the data. Uh, this is the triggering system of the ejection, where we use a transistor acts as a circuit switch, sending a small signal to the base part that opens the connection and powers from the power source to the ejection charge. Following a successful flights and data gathering, this is the app where we process the data, confirming that the data received in the ground station from the SD card, where we also have the data saved. This will be discussed later on by my colleague. So a silicon copper plated was used to make the mounting board. We manually etch this component. So this is where the components is soldered onto. This is the overall structure of the Avionics bay, where the Teensy-based flight computer and the commercial flight computer is installed. And this is the 3 Teresa rocket flights that we have for flight tests and data gathering conducted, and our testing designed flight computer. Also having a data on the commercial flight computer to be compared with. So here in the center is our Avionics bay. So for the price comparison of the two flight computer that both are having the similar components and functions. So as you can see, the Teensy-based flight computer is 3,400 cheaper than the commercial flight computer. So in the result that we gathered, the commercial flight computer is the basis of this percentage. Therefore, the RRC3 is the 100% data. So based on that, our pressure data in the Teensy is 99.91% compared to the RRC3. And the velocity, maximum velocity of our flight computer is 95.72%. And for the maximum altitude, our flight computer is 99.48% accurate compared to the RRC3. Overall, our flight computer is 98.37 accurate comparing to the commercial flight computer that we have. So here is the demonstration of our post-process using a MATLAB app and will be presented by my colleague, Christian Dave Beltran.
Good day, everyone. Here is our MATLAB application. For the first part, we have open file, which the user can choose to open a file, and then rearrange these numbers depending on the arrangement of their data. And then clicking load data will load all these data into the following section. For the altitude versus time, we have an apogee from the raw data, which is 653.24 meters, and the apogee from the simple moving average of 651.95 meters. For the flight data, we can see altitude versus velocity over time. For the velocity section, we have a velocity from the raw data, we have a maximum of 141.07 meters per second and the maximum velocity from the simple moving average of 115.15 meters per second. In IMU sensors or inertial motion units sensors, we have acceleration expressed in g, gyroscope expressed in degrees per second, and the magnetic field expressed in microteslas. And lastly, we have the Euler orientation. When we click play, it shows the recreation of the orientation of the rocket during flight. And lastly, for conclusion, the Teensy-based flight computer can be a replacement to the RC3 commercial off-the-shelf avionics system in terms of functionality, budget, and percentage accuracy in reading pressure, altitude, and velocity. With the open source nature of Arduino coding, the Teensy-based flight computer has an advantage of being openly accessible and customizable. The Teensy-based flight computer not only goes on par with RC3, but it also extends its purposes by being modifiable to carry more sensors and also save all data even before flight has been detected, thanks to its very large memory of 16 gigabytes compared to RRC3's 4 megabytes. And that's it for me. Thank you.